So this exercise related to nuclear decay and the binding energy. I have discussed till question 17 from this exercise. So we'll do from 17 onward. In question 18, in the early part of the 20th century, the Nobel Prize winner, George D. Lewis, made the first use of radioactive tracers. He studied the transportation of a small sample of isotope of lead in a broad beam plant. Complete the nuclear equation. So its emission of negative beta. So nucleon number does not change, it remains the same. Where proton number in a negative beta, it increases by 1. So this will be 83. The half-life of a lead is 3.83 into 10 to the power 4. What is meant by the term half-life? So half-life means time taken by half of the radioactive sample to decay. How much time half of the radioactive sample will take to decay or to be stable? That is known as a half-life time. So time taken by half of the radioactive sample to decay. That is refers to half-life. Show that the decay constant for a lead is about 2 exponent minus 5. Hence, then calculate the fraction of the original sample that will remain after 1 day, which is having 86,400 seconds. So how we can work out the half-life, how we can work out decay constant? Decay constant, we can use a half-life here, 3.83 exponent 4. So we know that like T half, the half-life is equals to 0.693 divided by lambda, the decay constant. So if we need the decay constant lambda, it is 0.693 divided by T half. So 0.693 divided by the half-life, which is 3.83 exponent 4 seconds. So we'll write as 3.83 into 10 to the power 4. This will give us a decay constant which is about 1.81 into 10 to the power minus 5 second inverse. The unit is second inverse, that's the reciprocal of the time. Now we need the what fraction is left after 1 day, which is 86,400 seconds. So if we say you use the formula n is equals to n naught e raised to power minus lambda t, where n naught is the original number of the atoms and n is the number of atoms after certain time. So we need the fraction. So we need n over n naught. So n over n naught is equals to e raised to power minus lambda t. And when we simplify n over n naught, e, the lambda we work out, that was 1.81 into 10 to the power minus 5. And the time, because this is in second inverse, the time should be in second. If it was in minute inverse, time should be in minute. If it's in hour inverse, the time should be in hour. So this is 86,400. So when we simplify this, n is equals to n naught is equals to 0.21. So point, like what fraction is left? We can say n is equals to 0.21 n naught. Like this fraction will be left after 1 day. Like this fraction will be left radioactive. As I mentioned, the question is show that the decay constant, hence calculate the fraction of original sample that will remain after, like what fraction will be radioactive. So it will be 0.21% of n naught. Or if we convert into percentage, we can also convert into percentage. Is it clear, this question? The energy release in these decay is 9.12 into 10 to the power minus 14. Calculate the decrease in the mass in kilogram. So we have the formula E is equals to mc square. We have the energy should be in joules whenever we use this formula. The change in the mass we don't know, and the speed of the light is 3 into 10 to the power 8 and then square. So it will be 9.12 into 10 to the power minus 14 divided by 3 into 10 to the power 8, then square, that will be delta m. So this will give us how much the mass has changed. It is 1 exponent minus 30 kilogram. The isotopes of the bismuth produced by the decay of the lead itself is radioactive. It produced both alpha and beta with overall half-life which is much shorter than that of a lead. Discuss how the decay of a bismuth isotope could affect the measurement made about the activity of a broad beam plant. So what they're saying, like example, if you have lead turned into bismuth, and lead was emitting out beta particle, but bismuth is emitting out alpha and beta particle both. But it has a short half-life. So how the results will be affected when we are measuring the activity. So the measured activity when we calculate it, the radiation will increase due to the presence of both alpha and, but alpha cannot pass through. Like example, what happened in a broad beam, as it is released, alpha will be stopped by it cannot pass through. Beta can pass through, so overall activity will increase because of beta. Not for alpha, you cannot say alpha, as alpha cannot penetrate or pass through that beam. If the same question was there and they say that bismuth which is produced is the alpha source and it is produced in a broad beam, then how the activity will change? In that case, there will be no change in activity because alpha cannot reach there. So mainly what happened when the lead turned into a bismuth, this bismuth is radioactive and it emits out both alpha and beta is radioactive, so it will emit out that. Like alpha and beta both are there, but alpha is having a short range, beta is having a long range, so it will give out or collect beta. So the calculated activity will increase. And don't say because of alpha it will be wrong. The activity will increase, and what is the reason for that? Because of beta particles from bismuth, not alpha. We don't say alpha. Why? Because alpha cannot penetrate or pass through the beam. Then after his discovery of element hafnium, that the George also discovered the element hafnium, which is a good absorber of neutron. And hafnium is sometimes used to control the rate of fission in a nuclear reaction, fission reactors. Suggests why a material which is good absorber of neutron enables the rate of fission to be controlled. Because how fission reaction occur? Fission reaction occur by absorbing the neutron, like the heavy nucleus break down by the help of a neutron. So if we reduce the number of neutron, the rate of like further fission will stop. As a result, what happened? Like fission happen or occur when a neutron targeted on the heavy nucleus, it break down into daughter nuclei and as a result produce more neutrons. So if we want to stop this, what we can do, we can absorb the neutron. So it suggests why material which is good absorber of neutron would enable the rate of fission to be controlled. So that material will absorb neutron, so it cannot undergo further fission reaction. Then fusion reaction could become a better alternative than to fission. Explain why this is the case and give reason why practical fusion reaction are still only at experimental stage. Like we know that the fusion produce enormous amount of energy compared to fission, and the fuel availability is like hydrogen availability is infinite as compared to uranium or plutonium. But still, it's not practical. It's still in the experimental phase, not in the practical phase. So first thing, fusion reaction produce why it is practically like why it is more useful than fission, because fusion reaction use hydrogen, which is abundant. That is one thing. And fusion reaction does not produce a radioactive waste as compared to that of fission reaction. And but the problem, the fusion reaction required very high energy and high density, and it need like we have to confine the plasma to undergo a fusion. So for that we need a very strong magnetic field, and we need a material which can hold or withstand a very high temperature. So the points you will mention, first thing, because we have to mention, give, explain with this, in this case, give a reason for practical fusion reaction are still. So why fusion reaction are better alternative? Because use hydrogen which is abundant. So hydrogen is abundant or in greater quantity. The second thing, does not produce radioactive waste as compared to fission. But the problem is we need high energy, like high temperature and high density. So for that, we need a material which can hold, like which can withstand at a very high temperature. Second, the problem is the confinement of a plasma. That is another, like to confine the plasma. So very strong magnetic field is needed. So the points, one mark when you mention fusion reactors use hydrogen, which is abundant. The second one does not produce radioactive waste. The third one, fusion requires high temperature and high density. Then the problem is for that we have to confine a plasma. And then for to confine a plasma, we need a very strong magnetic field. Otherwise, if it come in contact with the walls, the reaction instantly it will stop because the temperature will fall. So we don't have an optimum temperature for a fusion to occur.